Hello everybody. As you may know, during the lecture last week, after the break, for some reason I forgot to resume the recording, and the results were the part that we covered in the class wasn't unfortunately part of the recording that I posted last week. So in this video, I'm going to basically just repeat what I said in the class during the second part of the lecture last week. If you were in the class, there is nothing new here, so you can just safely ignore this. But for those of you who weren't in the class and watched the first part, make sure to watch this. And this will be helpful for the second quiz and the projects and all that. All right. So and then make sure that you watch the first part before watching this, obviously. Okay. So in the first part, we were start talking about branch prediction, and the last thing we said was we're going to use the history in order to decide about future branches. Okay. So the idea was that using the history, we can kind of say that, okay, what happens the last time is going to be used to decide what we should do now. So for every conditional branch, we're going to check the last time that we saw this branch. If the branch was taken, we're gonna predict taken this time. If the branch was not taken, we're gonna predict not taken this time. And we're gonna add this branch history table. This is just one bit, so we're gonna add this column here. And what we're gonna do is basically kind of like do the comparison and then do this and. That's the last thing I was discussing. Okay. And then if you want to show this as the finite state machine, and the FSM will look like this, right? So there will be two states. There will be predict not taken, and there will be predict taken, okay? So there will be two different states. If you are in the predict not taken state, it means that as a new branch comes, we're gonna predict not taken. If we are in the predict taken branch state, if we see a branch, we're gonna predict not, we're gonna predict taken, okay? So that's the prediction. Another thing that we do is that based on the actual outcome of the branch, we're gonna make some decisions on what should be the next state. So for example, if you are in the predict taken state, and if the outcome is also, so in the predict not taken state, we're gonna predict nothing, right? And now we see the actual outcome. So for example, during the fetch state, we're gonna predict not taken. The branch gonna go into the decode stage, and during the decode stage, we're gonna see the actual outcome. Was it indeed not taken? Or was it a mistake and we make a misprediction, it was taken? So we're gonna see that outcome, and then based on that outcome, we're gonna update our branch predictor. So we're gonna basically go back and update this bit here. And essentially what that means is that we're gonna switch from one state to another state if need be. So two possibilities happen. So either we predict correctly and the outcome was that. So for example, either we predict not taken and the outcome is not taken, or either we predict taken and the outcome was taken. In those two cases, we're going to stay in whatever state that we were before. There's no need to change, right? And then alternatively, the outcome might be the opposite of what we have predicted. So we predicted taken, but the outcome was not taken, or we predicted not taken and the outcome was taken. In that case, we need to switch. So we're going to update and we're going to switch. We're going to move from this state to this state, or from this state to this state. Okay, that's what we're going to do based on the outcome. So this is like a one-bit branch predictor with the finite state machine. Okay. The problem with this is that this does not really capture things that are changing quickly. Okay. So if I'm looking at this kind of the pattern, this is the actual pattern, and this is the prediction of that pattern. Okay. Let's say, for example, we are currently in the state predicted. Okay, so we are in this prediction state. Okay. So if we see a new branch, since we are in the prediction state, we're going to predict taken. Okay. But then we're going to see that the actual outcome is also taken. As a result, we're going to stay in the prediction state. Okay. Now the next branch comes, and then since we are still in the prediction state, we're going to predict taken. We're going to see the outcome and see the outcome is also taken. So we're going to stay. We're going to predict taken, outcome is taken, predict taken, outcome is taken, predict taken, outcome is taken. Okay, so far so good. We are in the one prediction, and the branch is kind of very consistent. It's always taken. Okay. Then we're going to get into this stage. Since we are still in the prediction state, if we see a new branch, we're going to predict taken. So we're going to predict taken here. But if the actual outcome of the branch is not taken, that is what we call a misprediction, right? So that's why I'm showing it with red. We predict taken, but in fact it should have been not taken. And if you remember, I told you that if we predict taken and we see not taken, we're gonna switch to the other state. Okay. So the next time we see the branch, we're gonna predict not taken. Okay. So this is next time we see branch, I'll predict not taken. And then the outcome of the branch could be many things. For example, the outcome of the branch could be indeed taken in that case. In other words, that will also becomes a misprediction. So this is a misprediction. This is also a misprediction. Okay. Well, what we will see is that now the outcome is actually taken. What will happen is that now I'm going to again switch from not taken to taken. That means that the next time I see a branch, it will be predicted taken, and in fact it is taken, and so on and so forth. So what I'm trying to tell you is that based on the current state, we're going to make a prediction. Based on the outcome, we're going to switch if need be. But with one bit, this switching happens very quickly. That as soon as we see a not taken, we're going to switch to the not taken stage. As soon as we see a taken, we're going to switch to taken state. Okay. In other words, our one bit kind of very, very quickly changes based on the outcome of the branch. And this may not be the greatest solution. So for heavily kind of like branch predictors, which is kind of like almost always in one direction, either taken or not taken, and maybe sometimes it's only not taken or the other way around, we only get like 80% accuracy, which is not the greatest that we can achieve in this case. Okay. For example, if you go with just always taken, we would have had 90% accuracy in this case, right? So it's not the greatest performance in terms of like heavily biased branches. And remember, many of our branches are heavily biased branches. So you want to have a branch predictor that can capture that behavior fairly well. Okay. So what do we do instead? We're going to expand our one-bit predictor to what we call a two-bit predictor, or in other words, we call it the bimodal. Okay. So what is happening in bimodal is that instead of having two states, we're going to have four states. Two of these four states are going to be predict states, and two of these four states are going to be not predict, or sorry, predict taken state, and two of these four states are going to be not taken states. Okay. So as I'm showing you in this picture here, let me just look at these. We're going to have basically these two states on top. We call it 0, 0 and 0, 1. This is just the numbers that we assign to them. These are basically what we call not taken states. Okay. So if we are either in 0, 0 or 0, 1, our prediction going to be not taken. Okay. If you are in 1, 0 or 1, 1, we're going to predict taken. Okay. So that's one. We're going to usually call this strong, not taken. And we're going to call this weak, not taken. Okay. And same here. So this would be strong, and this would be, the other one would be weak. Okay. So this would be weak taken, strong taken, weak, strong not taken, weak not taken. Okay. So that's one. The second thing is that how do we update this fourth state? So the update fourth state is basically going to be based on where we are. From 0, 0, we can only go to 0, 1. So if we are in the not taken state, in the strong not taken state, and the outcome of the branch is indeed taken, we're going to move from 0, 0 to 0, 1. And now notice that even if we are switching, we're still going to, for the next branch, we're still going to predict not taken. Okay. So that's the difference. So we're going to kind of add some resistance, some hysteresis to our prediction, that even though we will see a not taken or taken in this case, we're going to still predict not taken for the next branch. So it's kind of add a little bit of resistance, so not kind of like quickly flip-flopping between taken and not taken. We only switch from not taken to taken if we are here and we see a taken. Okay. So if we are here, sorry. If we are here and we see a taken, then we're going to switch from here to here. Okay. So we basically going to switch from a weak not taken to a weak taken. If we continue to see not taken, then we're going to switch from a weak to a strong taken. On the other hand, if I see that it's not taken, we're going to switch back to the weak not taken. So essentially, this part here is kind of like what one bit was, right? So this is basically the same one bit that we switch back and forth between taken or not taken. But now what we are adding is really these two strong taken or strong not taken, which what they add is that if you have a sequence of taken, 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 or not taken, not taken, not taken, then we're going to switch to this more stronger state and we're going to stay in those stronger states. Okay, so that's kind of the difference between a 2-bit heater branch predictor and 1-bit, and you can put and basically you can follow the same sequence that I gave you. Let's say, for example, let's say we start with like strong taken. Okay, so we start with 1-1, which was here. Okay, what we're gonna see is that we're gonna predict taken, 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 because we're gonna see this taken, taken, taken. At some point, we're gonna still predict taken, although the actual outcome was not taken. What will happen is that this will cause a switch from 1-1 to 1-0, which means that we're gonna switch from strong to weak. But as you can see, is that we're still gonna predict taken for the next branch. The reason for this is that still in the weak taken, we're gonna predict taken. And then we're gonna continue seeing taken, 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 which means that we're gonna switch to the strong taken. Basically, what this does is that it's always gonna predict taken because we start from a strong, we only see one not taken. In order for this to predict not taken, we should at least see two consecutive not takens. Otherwise, this will never predict not taken. Okay, and as you can see, is that the accuracy of this for more heavily biased branches is much better. In this case, it's 90%, and typically it's between 85 to 90%. Of course, the downside of this is that now we need 2 bits per branch. We used to be 1 bit, so in other words, we need more storage area overhead. Okay. So that's what we call a 2-bit branch predictor. Okay. So what happens after this is that there are tons of other research on branch predictors. Essentially, the idea is that if I want to make BHD more accurate, we either need to use a better kind of like a better mechanisms for history, for tracking history, or a better dynamic decision mechanism where I can predict that, oh, okay, this should be for this branch and that branch and so on and so forth. For this particular lecture, we're not going to go further than this, but I'm going to give you a few pointers. So there are various different ways that you can design a branch predictor. One way is what we call history of history, which basically we don't have just one history BHD, but we also have another BHD, which we call a global history, that keeps track of multiple locals. So for example, we separate branches from each other and we kind of treat their history from each other. We also kind of like treat them all as one group and then track them that way. So various ways that we can do that. There's another one called tournament predictor, which you have like a bank of different predictor and kind of do some form of a voting or dynamically decide which one to use. And then there are also other ways, such as you can use the compiler to help you with the branch predictor. Some program information, some debugging information for predictor. Of course, you can use machine learning for branch prediction, and that's what's been used a lot, because branch predictor, if you think about it, is basically a sequence of numbers, and you want to make a classification based on this sequence of numbers. So this is a classic machine learning problem, which you have, think about this as features in your input domain, and you want to basically have two class, 0 or 1, which 0 could be taken and 1 could be not taken. So this is like, classic machine learning problem. We can even have a more sophisticated machine learning problems, solutions for it, such as reinforcement learning and all that. And then we can have what we call a hybrid, which we can have like, a combination of various different things. For example, The latest and greatest branch predictor has been commonly used in modern processors called TAG, which kind of, it's literally just a combination of a bunch of these two-level predictors that we just described. Um, uh, so what we're going to do is we're going to give you project 2, and project 2 will be about designing a branch predictor. And there you're going to see that we're going to ask you to basically do a little bit of research on learning about these designs. Some of it I'm mentioning here, some of it you can probably find online. And you have to design your own branch predictor based on what you learned in the class and things that you will learn by yourself. So I'm going to have a separate kind of like a short video just quickly describing these different branch predictor designs. And then in your projects, you're going to actually learn more about that. Okay. So that's kind of the story of dynamic branch predictor. As I said, we're not going to go further in this for this lecture. Okay. But a few other things I want to quickly mention before we wrap up the discussion on the branch predictor. If you remember, we talked about various different types of branches. We talked about conditional branches and unconditional branches. And for the conditional branches, branch predictor basically helps that. For unconditional branches, BTB for fix that. For call, also BTB for fix that. But then if you have kind of indirect branches or return branches, which the target address could be many different addresses, we still don't have any solution. So neither of these things that we already discussed, including the BTB or BHD, going to fix this issue, unfortunately, because there are many target addresses these branches can take, and we don't know which one we should use. Okay. So I'm going to quickly talk about these two things. So we're going to use this thing called return stack buffer, RSB, which is going to help us to fix the problem for returns. Okay. We're still not going to fix the issue for indirect branches, but let's try to fix the return address problem. Okay. So what is this? The idea of RSB is this, that every return has to be preceded by a call. Okay. So there won't be a return without a call. So there should be a call first, and then there should be a return at some point. So what we're going to do is that we're going to use this stack-like behavior where when we see a call, we push the return address into some form of a stack. Like, let's say it's a dedicated stack. It's what we call return stack buffer. It's a particular buffer. We're going to push the return address into the stack. And since kind of call and returns are next to each other, the next time that we see a return, we can just simply pop the stack. And what we're going to do is, what we're going to get is this, that the return address here is for this call address. So we're going to actually jump exactly to where we're supposed to. And then if you have kind of like bunch of like calls, and then returns, what you will see is that this return and call are correlated, this return and call are correlated, and this return and call are correlated. In other words, Stacks does a great job for fixing this issue that we want. So all we need to do is that we don't need to use a BTB or BHC. All we need to do is that whenever we see a call, we push the return address into some form of a stack. Whenever we see a return, we pop it from that stack. We have to make sure for every single call and return, we have to push it pop. And this way, we absolutely make sure that this will work all the time. Okay. And then this usually, like, you only need few entries because at any given time, it's really just as short entries needed. For things like recursive, there are other optimizations that you can do. For example, you can do tail recursion, which means that you just keep popping the last address over and over again, and that will fix the issue of recursive functions at some point. And then final thing is the indirect branches. We're not gonna cover this in this class, unfortunately, but just keep in mind that there are dedicated indirect branch predictors that fix this issue. So this is more of an advanced topic. If you're interested, there are other courses in the grad level. We have like an advanced computer architecture class. I also teach an advanced and secure computer architecture class in grad. That if you're interested, think about taking it. I'm going to offer it in the spring, actually. So we can definitely talk about these things that time. All right. So that's it for the branch predictor. Let me pause because I also talked about superscalar in the class, so I'm going to talk about that as well. Just give me a sec. All right, so let's also quickly talk about superscalar processor. So if you remember so far, what we have discussed is how do we optimize a simple processor in order to improve performance. If you remember, we started like kind of a simple design of a data path controller, and we told you that a single cycle design would be all you need to do in order to be able to run a given ISA. But then we start kind of adding lots of optimizations. So we start with pipelining, but then we saw that, oh, okay, in order to actually make pipelining to work, we need to add forwarding and raw hazard and hazard detection and all that. Then we ran into control fluence problems and branch prediction, and we kind of like proposed the idea of speculation and prediction, and that will help us to further improve the branch prediction and generally improving the performance. And then we also talked a little bit about other ways that we can improve this, including the use of compiler and software. So now the question is, where do we go from here, and how do we further improve our design? In order to think about that, you have to go back to the CPU time formula and remember that we wanted to reduce this, right? So we want to minimize the CPU time. And if you remember, we had IC, CPI, and CT. For IC, I told you that there's not much you can do at the computer architecture level. What really you can do is reducing CPI or reducing CT. For reducing CT, all you can do is adding more pipeline stages or using newer technologies. That's what we always do. So we still keep adding more and better transistors, and that reduces CT. So that's kind of ongoing. But now the question is, can I do better for CPI? And for pipeline, you've seen that the best you can do is CPI is equal to 1. Theoretically, you cannot go beyond CPI equal to 1 because that's all you can do. You can always just essentially just process one instruction per cycle per pipeline stage, and that's the best you can get. Okay. So one question would be that, okay, why don't we add more and more pipeline stages? That way we can at least reduce the CT. The problem with that is that we're going to have what we call diminishing returns, which means that as we are adding more and more pipeline stages, at some points we're going to get more hazards, we're going to get too much complexity, we're going to get additional delays. As a result, modern processors only stays somewhere between 10 to 15 pipeline stages. They're not going to go beyond that for the reasons that I'm showing you here. So at best, what we can do is just adding somewhere between 10 to 15 pipeline stages. Beyond that, it's not going to really help us with making CT smaller, okay? So we kind of like hit the wall at some point where we no longer can add more pipeline stages, the CT kind of stays the same, and CPI is always equal to 1, okay? And then when CPI is equal to 1 means that IPC is also equal to, okay? And then another thing that you have to consider is that the reality is that CPI is usually more than 1. In other words, IPC is less than 1. The reason for it is that we need to have stalls, right? So for example, although we have forwarding, but for things such as load use hazards, we still need to stall. Or although we have branch prediction, our branch prediction is never 100% accurate. There are scenarios that we need to stall the processor, or we have misprediction and all that. So reality is that on average, our IPC is actually less than 1. It's not going to be even 1, okay? And CT is kind of like stable. This is what we call scalar pipeline processors. So the idea here is that obviously we can improve this significantly by changing this assumption about there should be only one instruction per pipeline and change that to what we call a superscalar processor, where you actually process multiple instructions at a time per pipeline stage, okay? This is what we call a superscalar processor, and what we are really doing here is what we call instruction level parallelism, or ILP. Instruction level parallelism is basically part of like a more generic term called parallel processing, which we can have different levels of parallelisms at the bit level, at the data level, or task level. These things we're going to talk later, but let's focus on this instruction level parallelism. So as I said, if you are able to process or issue multiple instructions per cycle, then we're gonna have what we have a superscalar processor. It will look like something like this. So like, you know, our simplified designs of pipeline. What we're gonna add now is that we're gonna, so this one is particularly showing that we can read two instructions at a time. So instead of reading one instruction, now I'm reading two instructions in the fetch state. Now I'm decoding two instructions in the decode stage, and as you can see, I'm basically reading two set of registers. So now I'm doing two registers. As you can see, I'm also writing two registers. And then since I have two instructions now, I need two ALUs, and basically many of these lines becomes two of them. Okay, so the idea is that can I basically change my data pattern controller such that I can support multiple instructions per pipeline stage. For example, this is kind of like a more detailed version of what we discussed. For example, we need to have multiple immediate generators, multiple ALUs, and so on and so forth. The idea is that can I basically be able to support two instructions at a time? But one thing to remember is that if I want to do that, you would say that, okay, this is as simple as just copying everything twice and be done with it. That's pretty much accurate, but there is also some considerations that you need to make. For example, you cannot duplicate many things. So for example, you cannot duplicate your register file, you cannot duplicate your memory, because there are two problems. One is that these are very expensive. You cannot just have two memories in the systems. And the second thing is that you want to have a coherent memory and register file. You cannot have like two separate register files that they don't talk to each other, because what if one, instruction needs to use the value of the other registers that's being updated on the other register file? So there is no notion of having two register files, but of course you can add more ports to your register file, or you can add more ports to your data, and so on and so forth. You can do those things, but you cannot just double everything without really considering these considerations. Okay. So here's what we're gonna do is we're gonna increase the port size of many of these systems. As you can see, the red arrows and red boxes and all these are the new things that we are adding. What you will see is that we only need one PC. The reason for it is that if you're always fetching two instructions at a time, we can always do two consecutive instructions. So for example, we can have PC and PC plus 4. So what we can do is that our next PC, instead of being PC plus 4, can be PC plus 8. So we maintain one PC, we always fetch two instructions, execute them, fetch another two instructions, execute them, and so on and so forth. But then we will have, kind of like other things can be doubled, including the number of registers that we read and write, which could be expensive. When I say expensive, I mean in terms of area overhead and power overhead. But again, we do all these things in order to improve the performance, and that's what we need to do in many cases. And then there are things that we can decide. For example, how do we design our ALU, and whether we need a particular ALU for load or stores or so on and so forth. But ideally, what this will give us is that we're going to have IPC equal to n, and n is the number of copies that we are creating. So for example, if it copies twice, like based on what I'm showing here, then my n would be equal to 2. In other words, now my IPC potentially can be equal to 2, which means that now my times is 2 times, my processor 2 times faster than the original one. And as you can see, I can basically feed these first two instructions, and then these two instructions, and then these two instructions, and so on and so forth. Okay, so that would be basically the idea of this superscalar. In reality, though, it's not easy to always feed two instructions to the pipeline. For example, if there is some form of a dependency between the instructions, we may not be able to feed the instructions. For example, this one is not, it's not a dependency, but what if, for example, we have something like this here, where your R3 here or X3 here and your X3 here are dependent to each other. So basically this one, the second one needs to read the value of this one. And remember, forwarding is not going to be helpful in this case. The reason for it is that these two instructions are at the same stage in the pipeline. So you cannot really forward from one to another, okay? So you cannot, quote unquote, what we call issue these two instructions. We cannot fetch these two instructions at the same time. And then there will be lots of checks if you actually make, so for the two, you only need to basically check these two registers with this register. But for example, if I have a 4-issue pipeline, which you have 4 instructions going at the same time, or 8-issue, superscalar, where you feed 8 instructions at the same time, there will be many checks, because now you need to check every source 1 and source 2 with every destination, and that creates a lot of problems in our pipeline processor. Okay, so the kind of long story short is that there are trade-offs. The good thing that happens with superscalar is that we can increase our IPC, and IPC could potentially, increase by a factor of 4, 8, 16, depending on how many times we want to replicate this. The downside, though, is that, this will increase the complexity. We need to do lots of dependency checking. And then lots of more hardware resources obviously is needed, because now we need to kind of double almost everything, which would be very expensive. And then the last thing would be, because of these dependencies and these problems, we may not be able to fully utilize all the lanes in our superscalar. So for example, if there is a dependency between this instruction and next instruction, I cannot kind of like issue this instruction. This instruction has to wait. So we're going to run this and then run this, and then we're going to run the next two. So we're kind of wasting a cycle here because of this. Okay. But generally, to kind of summarize, what is happening is that in scalar processors, at best we can do IPC equal to 1. But if we kind of using this instruction level parallelism and superscalar, we could tentatively provide IPC more than 1. The problem, though, is that there are lots of challenges that we need to address in order to be able to fully utilize this. And one thing that's really going to hurt us is the fact that we are just wants to kind of go with the program order and just fetch instructions one by one, and we want to check the kind of dependency of these instructions. So what we need to do instead is what we call a new kind of architecture called out of order execution architecture, that kind of tries to maintain this superscalar capability, so we can able to kind of feed multiple instructions to the pipeline at the same time, and while addressing these kind of dependency issues and these other challenges that we are facing in our design. Okay, so what we're going to do, and this would be basically the lecture that we're going to cover on Thursday, is going to be talking about how do we design an out of order execution processor where we fetch multiple instructions at the time, and we let them to get into the pipeline at different times and different order as we wish. Okay, so that's it. I'm going to talk to you guys on Thursday with the out of order execution. All right, thank you.